Okay, so we're going to talk about the gradients and directional derivatives. Okay, and so a way to think about what we're doing here is you think about having some sort of a surface, some sort of a like 3D surface, okay, and then you have some direction, and so you want to know like so if this is the phase plane down here, this is just the XY plane, and then this surface is kind of floating above. If I have some direction in the XY plane, what I want to know is, if I go in that direction, what is my slope of what is my derivative in that same direction? So I'm looking for this kind of slope as I go off in that direction. So I'm given a direction vector that may live like in the XY plane, but I want to find the slope of the surface moving in that direction. So you might think about like if you had like a topographical map, that had different kind of phase lines and stuff, and you're thinking about, okay, I'm walking around on a mountain. Maybe you're going hiking, and you're looking at a map that has these kinds of elevation changes on it. And you might say like, okay, if I go due north, right, then you want to say like, what is going to be my change in elevation? And so that's what we're talking about. We have this direction vector like on a plane, but we want to look at what is the surface doing? What is the rate of change of the surface if I move in that direction? So I'd be asking like, okay, how steep is it if I'm going to go due north from some point P? Okay, so, all right, so here is the theorem about computing the directional derivatives. So if f is differentiable at P, and U is a unit vector, I'm going to underline that because that's going to be important. A lot of times they'll give us a direction vector that's not a unit vector, so you're going to need to scale it down so that it is a unit vector. Okay, to have a unit vector, then the directional derivative of f in the direction of u is given by, okay, so here's the notation. This is the derivative in the direction of u of f at point P. So I'm going to write out in words what this is. This is the derivative of f in the direction of u at point P. So all of that is what that notation means, is equal to, I want to do the gradient of f evaluated at P dot with the unit vector. So this means the gradient of f evaluated at P, and then this is the unit direction vector. Okay, so let's just do an example of computing a directional derivative. So we'll just kind of follow the first example in the book. So I'm going to say, let f of xy equal x e to the y, and P be the point 2, -1, and then V equal 2, 3. Okay, so notice this point is in the xy plane. It doesn't have the y coordinate of the point. So a lot of times you'll have a point in the xy plane, a vector in the xy plane, and then you're going to be looking up at that surface that's kind of floating above. So you kind of keep this in mind. So this point is here on the xy plane. You have a vector moving in a direction in the xy plane, but then we want to translate that up to the surface and see like what is the slope of the surface at that in that place. Okay, so the way I compute it is I'm going to use this formula here. Okay, so I need to compute the gradient of f. So the gradient of f is going to be the partial derivative. So the partial derivative with respect to x is just going to be e to the y. The partial derivative with respect to y is just going to be x times the derivative of e to the y with respect to y is just e to the y. Okay, then if I took the gradient of f evaluated at the point P, I'm going to plug in these points for x and y. So I will have e to the minus 1, and then I'll have 2e to the minus 1. So those are that's my gradient of f evaluated at P, evaluated at point P. And then my v here, I notice that this is not a unit vector. So this is not a unit vector. So I need a unit vector pointing in that same direction. So the first thing I need to do is find the magnitude of v. Well, the magnitude of v is going to be the square root of 2 squared plus 3 squared. So that's 4 plus 9, which is 13, yeah? Okay, so that's not a perfect square. So what I can do is I can say my unit vector pointing in that direction is going to be 2 over square root of 13, 3 over square root of 13. And now if I took the magnitude of that, I would get 1. So my directional derivative in the direction of u of the function f at point P is going to be equal to, I'm going to take this thing dot with this thing. So it's going to be e to the minus 1, 2e to the minus 1. I'm going to do a dot product with 2 over root 13, 3 over root 13. Okay, and so when I do that, I'm going to get 2e to the minus 1 over root 13 plus 3e to the minus 1 over root 13, which ends up being, well, it ends up being 5 over e square root of 13. So that is slope. You know, maybe it would make sense here to do some sort of decimal approximation of that because I don't really have an idea in my mind of what that number is approximately. So if I got some sort of a number for that, that would tell me how steep this function is going in this direction at this point. So that would be the slope or the steepness in that direction. So another way to think about the gradient, this is as a theorem in the textbook, so interpretation of the gradient. If you remember that the dot product u dot v is equal to the magnitude of u times the magnitude of v cosine theta, where theta is the angle between the two, remember that? So in other words, if this dot product, or if this gradient is, or the directional derivative is defined as a dot product, I could also think about it in terms of you know, the magnitudes and the cosine. So if I have du f evaluated at P is equal to the gradient of f evaluated at P dot with the direction u, well, that's equal to the magnitude of f evaluated at P, of gradient f, magnitude of gradient f evaluated at point P times the magnitude of u, which it's a unit vector, that magnitude is just 1, times cosine theta, where theta is the angle between them. Okay, so this is going to be optimized. This is going to be optimized when cosine theta is equal to 1. So this will be maximized when cosine theta equals 1. Well, when is that? Well, cosine theta is equal to 1 when theta is 0. So what that's saying is that that the directional derivative is optimized when that unit vector points in the direction of the gradient of f. So in other words, the gradient of f will tell us the direction of maximum increase. So if we go back to thinking about like walking on a mountain, hiking in a mountain, if I want to know which direction to go to be the steepest, like straight up the mountain, the gradient is what will tell me what is the direction of maximum increase. And that just comes from this idea that this dot product is related to, the angle between the two vectors. And so cosine theta is 1 when that angle is 0. In other words, when the vector u is pointing in the same direction as the gradient. So the gradient is telling us the direction of maximum increase. So sometimes you'll see problems where they're asking, okay, which direction is going to be the maximum increase? Well, it's just going to be wherever the gradient is at that particular point P. All right, that's all for this one.